We're going to continue with our discussion in chapter 6. We're going to look at the logarithm and their properties. For all positive number a, where a is not equal to 1, when I have a to the power of y is equal to x, we looked at this before, this should be familiar, that's exponential function, is equivalent to y is equal to log of x with the base a. For those of you watching this later at home, this is the very first equation you want to include in your summary sheet. So if I have y is equal to log of x with the base a, you should be able to change it to its exponential function or vice versa. If I have it in terms of exponential function, you should be able to change it to the logarithm. So the expression of log, log, the symbol here for log, this a is the number which is the base of x. So log of x with the base a represent the exponent to which the base is a. So this number here is a base of your log, which would be the same base of your exponent. So let's do that. So my base goes right there. That's the base of my exponents when you want to transfer. Must be raised in order to obtain x. So the number a established, we're going to call it base of the logarithm, which is the same base as my exponent. And x is called argument. So this number here, x, this is known as argument. So I'm going to use different color for that right now. So this one here is my argument. So where does this x goes? That would be a to the power of y is equal to my argument. A to the power of y is equal to my argument. The few things that you can look at this to remember, one is the base of the logarithm. This number here that we write right below this symbol log would be the same number that we're going to copy for my exponential function. That's how you can remember. Now this number here, we just remember we call this argument would be equal to this. So this argument would be always front of this equal sign. Then y would be your exponents. So we really need to know how to convert from logarithm to exponential function and from exponential to the logarithm. We're going to look at some examples here. So these are some examples here. If I have log of 8 with the base 2 is equal to 3, that means 2 to the power of 3 is equal to 8. See, that should make sense. 2 to the power of 3 is equal to 8, right? Next one, if I have log of 16 with the base 1/2 is equal to -4, that's the same as saying the base 1/2 to the power of -4 is equal to 16. And that's true, 1/2 to the power of -4 is equal to 16 because this would be like 2/1 to the power of 4, which is equal to 16. Now this is going to show up quite a bit. You want to pay attention to this one here. Log of 5 with the base 5 is equal to 1. What's so special about this? You see the base is the same number as this number here. If this number matches, would be 5 to the power of 1 is equal to 5. 5 to the power of 1 is equal to 5. So we're going to see this as a tool to simplify when we solve equations later. So keep that in mind. But that's all we're doing right now is just converting. We say 5 to the power of 1 is equal to 5. If I want to convert this one, would be 3/4 to the power of 0 is equal to 1. And that should conclude that no matter what base I have here, log of 1 must be equal to 0. That would be the indication. Log of 1 is equal to 0. Doesn't matter what base we have. This base to the power of 0 must be equal to 1. Anything to the power of 0 is equal to 1. So let's go ahead and solve these equations. The first one, we have x equal to log of 4 with the base 8. In order to solve for x, I need to convert this to its exponential function. Remember, we said the base of the logarithm, which is 8, must be the base of my exponential. So it would be 8 to the power of x is equal to 4. So here we get to change my logarithm into its corresponding exponential by using the formula. And then now I can make the base the same like we did before. If it's possible to make the base the same, in this case it is, we can change 8 to 2 to the power of 3 and change 4 to 2 to the power of 2 and conclude that if the base are the same, then the exponents must be the same. So 3x equal to 2, so x equal to 2 over 3. That's all I did, was I changed it to the exponential function and made the base the same. For part B, I can do the same thing. Again, this would be x to the power of 4 is equal to 16 when I change it to its exponential function. To solve for x, we're going to take the 4th root of both sides. So x would be equal to 4th root of 16 plus or minus that would be x equal to plus and minus 2. We're only going to use the positive value for that. The negative doesn't make sense. For part C, similarly, we change that to its exponential function. 4 to the power of 3/2 is equal to x. X would be equal to the square root of 4 raised to the power of 3, if you recall. If I change this to square root of 4 and then raise it to the power of 3, which is 2 to the power of 3 would be equal to 8. So when there is no base here, it's understood that the base is equal to 10. So remember that. If there's no base written here, is 10, unless we see different numbers. So if you want to evaluate log of 12, or log of 0.1, or log of 3 over 5. For these values, you basically have to use your calculator. Just input the number into your calculator, and you should get these values. It would be a good idea to grab your calculator and see if you can confirm these results using your calculator. So this would be the example, one of the application problems using what we learned so far. In chemistry, the pH of a solution is defined as pH is equal to minus log of, this is H3O plus, that is hydronium ion concentration in moles per liter. The pH value is measure of whether your solution is more toward acid or alkaline, acidity or alkalinity. And that can be found if it is greater or less than 7, because the pure water has a pH of 7. So substance with pH value is greater than 7, they're more alkaline. But the substance that the pH value is less than 7, that would be more acidic. So either alkaline or acidic can be concluded from finding the pH of a substance. So it's a very simple process, really. So let's take a look at this example. You want to find the pH of a solution with given to us that H3O is equal to 2.5 times 10 to the power minus 4. And then we're going to determine whether it's above 7 or below 7 for our conclusion. So that's all we really need to do, is to use the formula pH is equal to minus log of this number is given to me as 2.5 times 10 to the power of minus 4. You could use your calculator to obtain these results. Later we're going to learn some properties of logarithm to break this down. But however, still have to use your calculator for part of that. But if you go ahead and enter these values into your calculator, you should get 3.6. Again, make sure you grab your calculator to confirm this result. So this is less than 7. The solution is acidic because this value is less than 7. We found it's 3.6. So we also want to find hydronium ion concentration of solution with the pH being 7.1. So in this case, they're giving you the pH is 7.1. You want to find, working this backward a little bit, you want to find the H3O plus, hydronium ion. So how do we do that? First thing is we eliminate this coefficient minus 1 by multiplying both sides by minus 1. So if you recall, when there's no number here, the base is 10. So I have minus 7.1 is equal to log of, when there's no number here, it means the base is 10. And this is the value that we're looking at here. So if I convert this into its exponential function, remember base 10 to the power of minus 7.1 is equal to what we're looking for. And this is about 7.9 times 10 to the power of minus 8 using your calculator. For all positive number x, this is called natural log. The symbol is ln. The natural log of x is a log with the base e. Remember the fixed number e we talked about? And the inverse property. Now, this two property is going to show up quite a bit in a lot of calculation. I suggest you write it down on your summary sheet. When the base of the log matches this number, the whole thing would be equal to, in this case, x. And that should make sense, because if I convert this to its exponential function, see, it would be a to the power of x is equal to your argument, which is a to the power of x. Or if you have a to the power of log of a, see how the base matches this exponent, so the whole thing would be equal to x. We're going to look at some examples on that. So in this case, if you want to calculate these values, again, you're going to use your calculator. Natural log of 12, you just substitute that in your calculator, you get the answer. In this case, natural log of e to the power of 10. You see, remember the base here is e, is matching the number, so this whole thing should be equal to 10, using that property. So as this one, this is my base, matching the base of the logarithms, this whole thing was equal to 84 then, in this case. All right, so those are the two properties that you want to remember. One is if I have, let's write it down one more time. If I have log of b, and then if it matches this number b, x, this whole thing would be equal to this exponent x. That's one of them. The other one, if I have b to the power of log of same base of x, that would be also equal to x. So these are the two properties that you want to remember. Let's take a look at these examples. First one, we have log of 1 is equal to 0. We want to find the base. We need to convert, right? With the a to the power of 0 is equal to 1. So in this case, log of 1 would be equal to 0. So log of 1 with any base is equal to 0, because a to the power of 0 is equal to 1. Second one and the third one is what we talked about. When we see these numbers are matching, the whole thing would be equal to k in this case. These are the three properties of logarithm. This is really super important. Make sure you write them down somewhere, everyone. If I have log of x times y, this is known as the product rule. We can write this as a sum of log of x plus log of y. Remember, the base are exactly the same. If I don't put any number there, it means the base is 10. So the first one is if I have log of xy, that's the same as log of x plus log of y. Sometimes I would ask you to expand it or write them in single logarithm. We're going to use this property. The next one is the quotient. If I have log of x over y, that would be log of x minus log of y. You notice that I'm not putting the base here to not make it too busy. So if I don't put any base, it means the base is 10. And the third one is the power rule. If I have log of x to the power of r, I can move this r right front of log and write as r log of x. Again, all this base here on the left-hand side are 10. And here to show the base could be anything. So if the argument is the product, quotient, or power of some expression, then we can expand them. If it's the product, we can change it to the sum of the log. If they are the quotient, if the argument is a quotient, then would be the difference of the log. And then if it's a power, we're going to move this exponents right in front of the log. So these are the three properties that you need to remember. So here it says, assuming that all variables represent positive real numbers, use the properties of logarithm to rewrite each of these. The first one, my argument is 8x, and that's a product of something here. So in this case, I can expand that to log of 8 plus log of x. That's how you expand it, because the argument is a product, use sum. Here, the argument is the quotient, so you're going to write it as a difference, would be log of 15 minus log of 7. You notice that the base would be the same. In this case, 9, the first one. We didn't write anything because the base was 10. Using the properties of logarithm, for the first one, we have log of square root of 8 with the base 5. So if I write this as 8 to the power of 1/2, this 1/2, remember, as a power should come right front of your log, would be 1/2 log of 8. Next one, 0.1 would be 1/10, which is 10 to the power of -1. So the -1 would be right front of log. That would be -1 times log of 10. So this is really is -1 times log of 10. What is log of 10 is equal to when there's no number written here? It means the base is 10, right? So that means that this whole thing would be equal to 1. This would be 1. Remember, when the base matches this number, the whole thing would be equal to this exponent. Recall log of b with the b to the power of x equal to x. That's what we're using again. So it's become -1. Last one here, we have to move 3 right front of 2. So this would be, actually this has come from one of those property, right? We have log of a to the power of log of x with the same base a. This whole thing would be equal to x. That's the property we learned. But as you can see, this 3 can come right front of that. It would be 3 log of 2, and this 2 matches, that becomes 1. So the whole thing is equal to 3. Again, these properties show up quite a bit. Make sure you write it down somewhere. We're going to continue using our properties for these. Here, my argument is a quotient, so I can write it as the difference would be log of x minus log, this would be log of x minus log of yz. Now, this one here is a product, so I can write it as log of y plus log of z. And then we're going to distribute this minus. You notice that I didn't put any base here to make it not so busy, but all the base are a. So you can see we get the same answer here as we have. So that would be distributing this minus would be minus log of y minus log of z. So we're expanding this. Next one, here's the power really, right? Because that is the same as log of m to the power of 2/3. I'm going to move this 2/3 right front of log, and my argument is just m. So at the end, you're going to look at your argument. If your argument is product, quotient, or power of something, you can expand them more. If not, you're done. Okay, this looks like we have to write this as exponential first. This is n. So here we have log of base b. That would be x to the power of 3, y to the power of 5, or z to the power of m to the power of 1/n, because this exponent, this was 1/n. So I'm going to move this 1n right front of the log, and here I can expand this because this is the quotient. I'm going to write this as log of x cubed y to the power of 5 minus log of z to the power of m. At the top, we can expand it to the sum because the top is sum. So here would be 1/n log of x cubed y to the power of 5 minus log of z to the power of m. And this 1/n belongs to both of them. So now this portion here can be written as the sum, like we're doing. So now I'm going to move all the exponents right front of the log. There are 1, 2, 3 of them. Should go right in front of that. And then we can distribute this 1/n if you want to. And that's how you expand them. Use the properties of logarithm to write each expression as a single logarithm. And I'm going to do it backward. These are expanded. You want to write as a single. So for part A, this is a sum. So these two can be written as the product, the argument, the product of the argument, and then here would be the quotient. So this two can be written as log of x times x plus 2 with the base 3. And then this two would be the quotient, would be the argument over 2. So that's how you would change it into a single logarithm. Next one, here I need to move the 2 right at the top of m. So as the 3 goes to exponents for n. Now the argument here would be m squared minus n cubed. Recall minus means the quotient. So we're going to write it as log of m squared over n cubed. So you should be able to do this back and forth, write it as a single logarithm or expand it like we're doing. Okay, in this example here, if I want to write as a single logarithm, I'm going to move this 1/2, 3/2 right front of the exponents here. There's no coefficient for the last one. So the first one would be log of m to the power of 1/2, log of 2n to the power of 3/2. Okay, now these are sum. The arguments should be a product, and then the next one would be minus means would be the quotient. So that's how you change it into a single logarithm. So that would be 2 to the power of 3/2, n to the power of 3/2. Then we can do some simplification here because we have n to the power of 1 here, and then here we have n to the power of 3/2. We can subtract them. So we'll see how to get this one. So this would be really is log of m to the power of 1/2, 2 to the power of 3/2, n to the power of 3/2 over m to the power of 2, n to the power of 1. So here, if you recall, if you have a to the power of n over a to the power of m, that's the same as a to the power of n minus m. That's what we're really doing. So in this case here, for the m part, would be m to the power of 1/2 over m to the power of 2. That's the same as m to the power of 1/2 minus 2 over 1, which is equal to m to the power of, the LCD is 2. So if I multiply this by 2 over 2, that would be m to the power of 1/2 minus, this would be 4/2. So it would be m to the power of minus 3/2. You see, this would be the same as 1 over m to the power of 3/2. You see how m to the power of 3/2 went to the bottom of the fraction? That's why. Okay, for the n, we do the same thing. If I have n to the power of 3 over 2 over n to the power of 1, that's the same as n to the power of 3/2 minus 1, which is n to the power of 3/2 minus 2 over 2. The LCD is 2. So it would be n to the power of 3 minus 2 equal to 1/2. That's why this stays at the top of the fraction, because its exponent is positive and the rest is here. So that would be log of 2 cubed, n to the power of 1, m to the power of 3, the whole thing to the power of 1/2. If you want to write it this way, you can too. Which is really is the second root of 2 to the power of 3 is 8n over m cubed. You write it in as a single logarithm this way. This is also a very useful formula. It says that when the base here is not 10, you can write this as log of x over log of a, and we can pick any base you want here. You can change it to any base you want. So obviously, if you want to use your calculator, you want to use 10, right? So if I wanted to know what's log of, let's say, 5 is with the base 9, now my calculator only evaluates base 10. The calculator doesn't give me what's log of base 9 is. So I can write this as log of 5 over log of 9, and then pick any base I want instead. Of course, I'm going to use 10. So now if I divide log of 9 by log of 5 using my calculator, that would be really is log of 5 with the base 9. So that's how you use this formula here. So in this case, we have log of 17 with the base 5. So I can write this as log of 17 over log of 5 and then change it to the base 10. So I can use my calculator. Or you can even use natural log, give you the same answer. I can use your calculator, as you can see. Make sure you verify these results using your calculator. So here we have log of 0.2 with the base 2. My calculator only evaluate base 10. So I'm going to write this as log of 0.2 over log of 2, and then use base 10, or you can use natural log. As you can see, you get these results using your calculator. This would be a word problem, application problem, modeling the diversity of species. Larger area of land tends to have greater number of different species of animals than do smaller area of land. One measure of diversity of species in an ecological community is the index of diversity is given to us as this formula. You don't have to memorize this formula. The formula would be given to you for this problem. So in this application problem, they're giving to us a formula. H is equal to minus P1 log of P1 with the base 2 plus P2 log of P2 with the base 2, and so on, where P1 and P2 and all the way to Pn are the proportions of a sample belonging to each of n species found in the sample. So in this case, it says find the index of diversity in a community with two species, one with 90 members and the other one with 10 members. Let's see how we're going to use this formula to solve this. So since there are only 10 since there are a total of 100 members in the community, so P1 would be 90 over 100, which is 0.9. P2 would go to 10 over 100, which is 0.1. So now I'm going to use my formula because I really need to find log of 0.9 and log of 0.1, and I can convert this with the whatever base I want. I can change this to natural log of 0.9 over natural log of 2, and here I can convert this to natural log of 0.1 over natural log of 2. Recall, we're using this formula again. If I have log of x with the base b, any base b, I can write this as log of x over log of b, or I can write as natural log of x over natural log of b. That's what we're using here. And if I use the log, I'm going to use base 10, so I can use my calculator. So now I'm ready to input these numbers into the formula is given to me. And you would find it's equal to 0.469. So the conclusion here, if two species are equally distributed, the measure of diversity is 1. If there is little diversity, h is close to 0. So in this case, we find h is equal to 0.5. So there is neither greater nor little diversity in this case.